Hello, welcome to FX PhD. My name is Matt Leonard, and over the next 10 weeks we're going to be looking at our new Maya Foundations series, Look Development and Lighting. So we're going to be covering a whole host of topics, including things like lighting concepts and stages, high dynamic range lighting, look development, optics to do with cameras and lenses, compositing and deep compositing. But this week, week 1, we're going to start by looking at color theory and pipeline. Now, before we get going, I'd just like to point you in the direction of this paper. It's written by a friend of mine, Jeremy Seeland, who used to work at Sony Picture Imageworks, and it's called Cinematic Color. This has been the basis for this first week. It's incredibly useful, and Jeremy has really done a lot of things over the years while he was at Sony. He co-wrote Katana, which in itself is a massive feat, and he's also written Open Color I/O that a couple of years ago he won an Academy Award for. So his paper has really become a backbone for this first class, and I would highly recommend you having a look at it because it really fleshes out everything we're going to talk about in this first class here. So let's begin by looking at methodologies. There's lots of different ways in which we can manage color in a VFX pipeline. Weta may be doing it differently to MPC, ILM may be doing it different to Framestore. Each company is going to work the way that they think is going to give them the best possible quality for the color that they're working with. So you've got questions like, do we render in high or low dynamic range? Do we work with gamma? Do we linearize the gamma, or do we use a gamma of sRGB 2.2 for instance? Do we use display LUTs, or do we not need to use them for our pipeline? Do we use a wide gamut or a small gamut? And do we work logarithmically or linear throughout the pipeline? All these questions are really important, and they've changed over the years. And depending on how the data is coming into your pipeline and how the data is going out, it's really going to determine what of these you're going to implement into the pipeline that you're using. Now, today, many companies are moving towards a physical-based look development and lighting workflow. And what this means is that they're using plausible lights, physically based shaders, and physically based rendering. And all these require the pipeline to be a HDR or high dynamic range based or scene referred based color pipeline. And this is becoming very important to make sure that everything is going to work out and look the best as we move through from one program to the next and give us the final images that we need. Now, one of the things we have to think about are the multiple sources of information that are going to be coming into our pipeline. And depending on what you're doing, you're going to have lots of different things coming in, probably just for one show, let alone all the projects and all the shows you're going to be working on. So for instance, is the footage coming in as a film camera, or is the footage being shot digitally like on the Red or the Alexa? Are we getting material from a digital SLR camera for maybe textures, that kind of thing? Are we using bracketed high dynamic range images? Are we painting high dynamic range images or low dynamic range images? And are we getting information from our clients, source material that they're giving us that we may or may not know the origin of? So there's many different sources of information coming into our pipeline that we need to manage and understand what they are so that we can use them to the best of our ability. Now, on top of the information coming into the company, we also have a complex internal pipeline that we tend to have to manage as well. So you've got things like Photoshop and Mari for doing paintwork. You've got Maya, Houdini and Katana, Clarice for doing lighting and rendering. Render engines are obviously massive. We've got Arnold, RenderMan, V-Ray, and then when it comes to compositing, we've got things like Nuke, Fusion and After Effects. They all work slightly differently, and we all need to manage them. Then on top of that, we have a huge amount of proprietary software depending on where you work. So ILM obviously has its base backbone pipeline Xeno. Disney have their own renderer. Weta have Manuka. Rhythm and Hues has Ren. You've got B Studio from Birth, and Double Neg have their own system too. So not only have you got software off the shelf that you're trying to manage and understand, but you've also got internal proprietary software that you're trying to manage and understand how that works within the color pipeline as well. At the end of the day, what we're trying to get out is robust imagery. And the reason why it needs to be robust is because visual effects are not the end of the pipeline. Following visual effects is often a DI or digital intermediate process, and so our VFX images need to stand up to sometimes what becomes dramatic color grading. There needs to be enough information in our shots for both manipulation and for the original content not to get lost. So often we'll see that a lot of grading is done on top of what we're doing, and we need to make sure that when the color grader starts pushing and pulling the images around, that the information is there and isn't going to band or just disappear. So we need to make sure that the images we're producing are robust enough to have this kind of work after we finish with them done to them. Now, a good place to start in understanding all this is a bit of color science. So color science basically begins with spectrum, and that is the information regarding light. Light energy is measured as a function of wavelengths, or NM for short, and the human eye can see between 380 wavelengths and 780 wavelengths. And you can see from this diagram, I've put those two white lines so you can clearly see what's going on. Either end of that is still information, but we're not able to see it under normal circumstances. So at one end, down at 350, you've got ultraviolet information, and right at the other end, at 800, you've got infrared. So all of this is visible light or existing light that can be photographed, measured, or seen, depending on what the situation and what the apparatus is. Now, the human vision system under normal circumstances is what we would call trichromatic. And colour can be fully specified as a function of three variables that we can see in this diagram labelled as X, Y, and Z. And this information basically has been mapped into what's now known as the CIE 1931 colour matching function. And the system converts the spectral energy into a measurement of colour. Now basically these colours can be replotted and converted into a horseshoe-shaped region, and the edge of the horseshoe region is called the visible locus. This corresponds to the most saturated colour spectrum that can be created independent of luminance, and the luminance is usually represented by capital Y. So in this image here we actually see the whole of that visible locus, that information made into this horseshoe shape with Y right in the middle, which is obviously the luminance. Now depending on the application that we have and the information that we need and have available to us, we're going to get various different gamuts out of this block of color that we have available. So remember, this is everything that is visible to the human eye and can be measured. So this is all of the color spectrum information that we know of. But depending on what you're doing will depend on how you actually can use and harness that information. So the way this works is you basically add this triangular shape that shows what can be used. So on this first slide, you can see this is the visible spectrum. So this is where we're losing information in both the infrared and the ultraviolet. And this is the visible spectrum that we have. And in the middle, where that luminance point is, that's the D65 white point. Now when it comes to computer graphics, we're obviously also going to be working in a gamut, but the gamut that we have is not the visible spectrum. So quite a common one would be this one, the sRGB gamut, and you can see it actually uses a very small amount of the information that is available to us. Now this often confuses people because you can make the statement, I'm working in linear sRGB. And if you think about that and you weren't aware of gamut, that could be confusing, because normally when someone says we're working linear, you're thinking it's linear in that we're going from 0 to 1 as a straight line, and we're thinking of gamma. If you said sRGB, you're obviously thinking usually of a gamma 2.2. So for someone to say I'm working in linear sRGB, if you're unaware of this gamma, it can seem very confusing. How can you work linear and sRGB if you assume both of them are talking about linear or gamma corrected information? What they're actually saying is that they're working in a linear color space, but the gamut that they're using is this section of color, which is defined as sRGB. And this is one of the smallest amounts of information from the overall color spectrum that you can use, sRGB. Now you can increase that by changing your gamut from sRGB to Rex 709 or HDTV, and that uses a larger amount of information. The gamut appears larger. You also obviously have something like Adobe sRGB, which is again larger still, or you can go all the way up to the CIE RGB, which uses a huge amount of the visible spectrum available to us for our computer graphics. Now, let's go back and actually talk about what RGB actually is when we think of it in color terms. So RGB is basically a color encoding system that uses primaries where red, green and blue are mixed to create a range or gamut of colors. So that's what RGB is. It's the primaries that basically create the gamut or range of colors. The look of these colors are tied to the display device, and colors are often displayed in a non-linear way. So when we have a monitor that you're probably looking at this video on, what you're almost certainly going to find is that monitor is working with a sRGB value. Now these colors can have both direct or indirect relationships to real-world units depending on how you're working, and we refer to this as the image state. Now, color spaces that have been designed specifically for display characteristics such as your monitor, the cinema screen, your iPad, they are what's known as display referred, whereas color spaces designed for input devices are called scene referred. So display referred imagery is defined colorimetrically with regards to an image as shown on a display. Display referred imagery has a dynamic range which is directly tied to the display, so you get the best look of the image based on the display that you're viewing it on. So a cinema screen will have a different setup to a monitor, and a broadcast monitor will have a different setup from your TV at home, for instance. So it's specifically designed to give you the best viewing information of color for that display. Now for standardization purposes, sRGB, or what's known as standard RGB, can be used for an average RGB display monitor. So this is what we're talking about when we discuss Gamma 2.2. sRGB and Gamma 2.2, they're not exactly the same. The curves are very slightly different for the Gamma, but it's near enough. And displayed referred imagery often requires linearization, and this can be done via a gamma function, obviously, which can be usually an invert of the display limitations. So we know, and we've talked about in other classes, that when you put an image onto your monitor, the monitor, because of the hardware, darkens the image down. So we use an inverse gamma of 2.2 to brighten the image so that when it then is displayed correctly on the monitor, we see those values as we intended. Okay, so that is display referred imagery. Scene referred imagery defines the color values proportional to the real world. So we're talking sun, sky, land, that kind of thing. There is no maximum white point in scene referred imagery. Obviously in displayed referred imagery, the maximum white point is usually a value of 1. That is where the white hits, and if it goes higher than that, it just clips at 1. In scene referred imagery, you can go beyond 1, and often do go way beyond 1 if you're looking at, for instance, a bright sky or especially the sun. And the color pipeline is normally linear, so you're not using gamma in order to kind of organize your information. And increasing or decreasing values are often referred to in terms of stops. So when you're dealing with scene referred imagery, you will talk about upping or downing the image's brightness based on stops, same way that you would discuss it in a photographic term. And it's very specific about that, because often when we're talking to cinematographers, when we're talking to colorists, they understand that if you go up a stop, you double the light. If you go down a stop, you half the light. So it's a terminology and a reference that we all understand. So that's scene referred imagery. So in this example, we can basically see stops versus pixel luminance. So if you have 0 stops, you could say that the pixel value is at 1. If you go up half a stop, you're going to go up a value of 1.4.4. If you go up a whole stop, you're doubling the light to 2, doubling the information to 2. If you go up 2 stops, you're going to 4, 3 stops going to 8. And if you went up 8 stops, your value of 1 goes all the way up to 256. And it works the same. If you go down 1 stop, you're halving the light from 1 to 0.5. If you go down 3 stops, you are obviously going down to 0.125. And if you go down to 8 stops, you're getting incredibly dark, but the information is still there. And that's what's important about this. It doesn't matter how many stops you go down, you're still going to have information there. You will never get pure black. It's in fact almost impossible to get pure black, because the more you stop down, the darker it's going to get, but it will never ever end up at 0. Now this next diagram is really interesting because it really helps us to understand the vast difference between what we may think is bright and quite bright and just average. So the first column on the left hand side is luminance, and this is based on candela per meter squared. The middle shows you the relative exposure, obviously in stops, and then on the right is the object itself. So let's just begin by looking at some of the base values. Relative exposure of 0 would be white paper in a typical office lighting environment. So probably where you're sat now watching this, if you put some white paper on your desk in a regular lighting situation, that's going to have a relative exposure of 0, and the luminance is going to be at around 100, and that's 100 candela per meter squared. Now if you went outside and looked at the blue sky, you would have a relative exposure of 5.6, and your luminance is going to go up to 5,000. So the difference between the blue sky and the white paper is obviously a lot, from 100 all the way up to 5,000. Now if you took your piece of paper out of the office and went and put it outside, the white paper in the sun, the relative exposure then goes up from 5.6 to 6.6, and that then goes to 10,000 candela per meter squared. Now if you take your camera and you face it up at the sun, the difference is huge. So remember, we have our white paper in the sun. The luminance of the sun on the white paper gives you a luminance value of 10,000. Pointing the camera at the sun itself, if you could measure it, will give you a luminance value of 1,600 million candela per square meter. So it's absolutely huge, the difference between the blue sky at 500 and the sun itself. And obviously if we're dealing with display referred information, this is just impossible to capture. So if you imagine taking a shot of the blue sky and the sun, the chances are the sun is going to end up just hitting the max, and you're going to end up with it just kind of clipped. If you then took that image into Photoshop and you put your color picker on the sun itself, it's going to come out at 1. If you then move the color picker across to the blue sky, the chances are it's going to come out at something like 0.85, 0.9, something like that. So the difference in display referred information between the sun and the blue sky is only about 10-15%. However, in scene referred information or real world information, the difference between the blue sky, which is at 5,000, and the sun itself at 1,600 million is a much greater amount. And that information can only be captured and used if you're in a scene referred color pipeline. So the question obviously comes up, how do you take scene referred information and actually display it on a monitor? Because that's obviously what we want to do. Well, there are a number of different ways of doing it, but one of the most common ways is to do it using an S-curve, which you can see here. So we know that most displays can only represent a relatively low dynamic range, LDR, low dynamic range information. There are some HD monitors or HDR monitors out there, but most of us don't have them. Direct mapping of high dynamic range information to a low dynamic range display often produces pretty unpleasant results. So one method, as I said, is using this S-curve, which can be called tone mapping. So basically what you do is you round off the brights and the darks and you keep the middle information. Now, I said that you can cause some problems in doing this. Some of the problems are these. If you are using scene referred information, filtering, anti-aliasing, and the use of negative lobes, which you can see in the diagram at the bottom, can often cause ringing, so you need to be careful with that. Also, you have to use 16-bit color depth as a minimum to capture the information, and the storage requirements for using that 16-bit color depth really goes up to quite a significantly large file type. So you need to be careful of ringing information for filtering using negative lobe filters such as this Riffman filter, and you also need to use at least a floating point file format. Maybe it's half float or full float, but it needs to be 16-bit. You can't really do it with 10-bit, 8-bit, or even 12-bit. Now, sometimes you can't store your information as float, and you may end up having to store your high dynamic range information as integer values. So, logarithmic, or what is often referred to as log encoding, allows for many of the benefits of floating point without necessarily having to go to that 16-bit. You can often do it with 10-bit by encoding information in a clever logarithmic way. One of the things that happens though with log is that the midtone pixels reside in the middle portion of the encoding space, and therefore if you directly map a log image to an sRGB monitor, you end up with the image that we have here of Marcy that appears very low contrast and washed out. The other thing that's really important when dealing with log images is to know and remember that not all log images are the same. Obviously, if someone gives you a floating point image that's linear, you know that linear is linear, you're good to go, you know what to do with it. If someone gives you a log image, however, it may not and probably isn't the same as the last one you got. For instance, slog, redlog, ARRI-log-C and Cineon log are all different flavors of logarithmic encoding, and the curves that are used in order to store that information in that logarithmic encoding space is going to be different for each one of those manufacturers and each one of those encoding methods. So you need to make sure that when you're dealing with log that you unencode it and work with it using the right slog, redlog setup, etc. for the specific information that you have. Now, when we're talking about the feature film color management pipeline, we're really talking about a number of things, including shading, lighting, and rendering. That's obviously one of the core areas of our pipeline for visual effects. Compositing obviously sits at the end before we pass it off to DI. But what we want to do in order to work and produce the most physically accurate lighting, shading, and rendering, we need to be working in our high dynamic range scene, linear, or scene referred color space. What we should do is we should have all our images ideally converted to linear color space first. So if we're taking pictures with our Canon D5, we want to linearize them before they get put into the pipeline. If we're getting information from the Red camera, ideally we potentially want to keep it or convert it into linear. And when we're rendering out of our renderers, whether it be RenderMan or whatever you may be using, we want to make sure that what we're rendering out is linear as well. We don't want to be rendering out with sRGB or anything else that may be adding additional encoding on top of our image. Linear out of the renderer is the best way and really the main way that major companies are working now. When we are obviously wanting to view that information, we're going to be viewing it maybe in dailies on a cinema screen, we may be viewing it on our monitors, our desks, but then we're going to need to add a viewing transform or a LUT on top of that so it displays the correct way. So everything needs to be linear, and then when we display it, we want to make sure that we're adding a viewer transform or a LUT on top of that so it displays correctly to look at it and we know what we're doing. Now, before we move away from our presentation and we get into Maya and actually look at how do we work with our linear color pipeline inside of Maya, a couple of additional things that are worth just mentioning. Firstly, ACES. ACES stands for the Academy Color Encoding Space, and it's obviously created by the Academy of Arts and Sciences. And ACES is a new workflow which stores the data firstly in an OpenEXR format. The color space that it uses is high dynamic range scene referred linear space. It has a mid-grade point of 0.18 or 18%, which is exactly what we want. And it basically contains a color gamut which is as large as the visible spectrum. You can see on the diagram on the left-hand side, the ACES gamut covers the entire horseshoe, and it's the only gamut in existence at the moment, as far as I know, that does that. That means that if we convert our information to an ACES gamut, we are not losing any information as we color correct, as we work with our images, and when we render things and create things, we have the entire spectrum of information that we can use and have at our disposal. Now, obviously, that is a huge amount of information. So the Academy has come up very recently with a new version of ACES, which is called ACES CG, which is a smaller gamut, and that still is going to enable us to work in a much more precise way than that which we would have done in the past. So that is ACES. Also, we mentioned much earlier OpenColor.io, written by Jeremy Seelan at Sony Picture Imageworks. OpenColor.io is an open source color pipeline. It's integrated into a lot of software. Nuke has it, Mari has it, Katana has it, Maya has it. It basically has two major goals: consistent color transforms across multiple applications and pipelines. So basically, when you say that you want the color transform to be this, it's going to be that across everything. So we're not dealing with an sRGB that's been set up by Adobe, sRGB that's been set up by Autodesk, sRGB that's been set up by the Foundry. It's set up once, and all the applications that we know and love are going to use that one color transform that's going to be the same across all the applications, and that's going to give us consistent image display across all of our applications. So obviously we want to make sure that when we are in Nuke and in Maya and in Katana and we're looking at our image and we're saying that we have this LUT on, we want to make sure that that LUT is going to look the same across all the programs. There's no point in putting one LUT on Maya and then having, say, a Foundry LUT that we think should be the same but is actually slightly different. Then we're going to not see the information clearly and accurately represented and reproduced. So the OpenColor.io open source project, which is really useful, really good, basically creates a consistent color transform and image display across all those applications. So that again is really interesting and well worth looking into. So from here, let's move out of our slides and move briefly into Maya and then into Nuke, so you can actually see how does this work, so that you can work inside of Maya as we're doing our color and look development, and we will know then that we have got a consistent high dynamic range, scene referred linear pipeline for everything we're doing moving forward. Okay, so here we are over in Maya 2016. I'm just going to load up a scene that I've made previously, and this is obviously going to be available. So what we're going to have here when this loads are two cards. We've got this one here, and this one you'll see if we come across is a surface shader, and what we have on it is this scene referred 32-bit linear EXR file. And then we also have, if I hide that and show this one, another card. You can see this one if we come in and just look at the file. This is a display referred 8-bit sRGB, so not linear, JPEG. And here are the files that are going to be in the source images folder. So this is the JPEG. You can see if I display it, that's what it looks like, a little bit off your screen. So regular Macbeth chart. And on the Mac, you can see this is the OpenEXR file, and you can see it looks slightly different because, as you probably know with the Mac, the images end up washed out because it doesn't know what to do with the fact that it's linear. So that's just a issue with the Mac operating system. But this file is 14.8 meg, 32-bit, and this one 8 meg is 200 kilobytes. So what we've got is with this first one, if we come in and look at the texture, you can see that here we have in the file name or the file node this color space, and you can see it's set to sRGB. If I switch across to the other one, you can see that this one, if I select it and come into the file, this is set to RAW, and there's a whole bunch of different things that you can set this to, but RAW is the right one. That basically means it's linear. So if I go ahead and render this one, so if we look through the camera and we just make sure that we are looking at the kind of render window clearly, and I do a render of this, you can see there's our image. So I'm just going to save that. I'm then going to hide the scene referred one and show the display referred one. And again, just need to make sure this is set to show us the whole thing. It's a little bit out because obviously we're not on the attribute editor. Come back, it looks fine. So I've saved this one. This is now going to be the next one, which is, we just move up, you can see this is the EXR. So if I render this, you can see straight away that the colors are exactly the same. I'll be able to save this one here and move back and forth. You can see we're getting exactly the same set of colors. Now if we go into the settings here under window and settings and preferences, just close this down, move this up so you can see it. They've added this new color management section here. So at the top we've got the ability to enable color management, and you can see as we're doing that, it's making a difference both in the viewport and obviously in the render. So if we switch back across to our scene referred and again switch that on and off, you can see it's making a huge difference here. So with this on, we're actually getting the color management taking place. Now we can also use Open Color IO input color space rules if we want. And we're going to need to then use the Open Color IO configuration, which I've put in here. Okay, so you can see this is just coming shipped with Nuke, this particular one, and I've just copied it out of the Nuke folder and just placed it there. So if we want to go with this, this is now going to use Open Color IO to do our configurations and our color space. So I'm going to turn those off. I don't want to do that, but it's there if you want to. Next we've got our color transform preferences, and basically this is what gamut do you want to use. So if we leave it on the scene referred, then that's going to use the smaller gamut, the Rec 709 sRGB gamut. We could go, if we wanted to, all the way up to our main ACES gamut, the really large one. You can see that makes quite a difference in what we're seeing. Or we could go down to ACES CG. And you can see again we're getting a different look based on that gamut being used. I'm going to put it back to just using the Rec 709 there. Then we have our viewing transform. This basically is like the LUT that takes place for everything that we're using. So if we want to go with log, you can see everything goes that kind of washed out color because that's obviously logarithmic. If we go raw, everything goes dark because we're now looking at it without any lookup table on. And if we wanted to go with the most straightforward one, we could go with gamma 2.2 or possibly sRGB. They're really close, but as I said before, the curves are very slightly off. Okay. Then you've got, if you want to, this input color space set of rules that you can apply. And you can then also apply output color transform preferences. So this is basically determining whether you bake the information into the file or whether it just is applied at the play blast level. Okay, so we want to keep this off because we want what we want to render out to be linear. I could obviously choose raw here and put this on, and that's really going to achieve the same thing. But I'm just going to leave it off, and what we'll get out will be pure linear. Other things we can do is just set the transform LUT path directory, and they've given us some LUTs here already. And we can also do things like show the color management pots if we want to. And that enables you to basically color correct things like the color swatches and bits and pieces like that. So I'm pretty happy with that. When you first start Maya 2016 and you make a new scene, it sets all this up pretty much for you. The only thing you really need to look at is just deciding whether you want to increase your gamut. But for what we're doing, I'm just going to leave it on that. Okay, so if I save this out, I'm going to come in now and I'm just going to render out these two as two separate render files, and then we'll load those into Nuke and compare them with the original. And what we should be getting is two outputs that look exactly the same as the original scene referred 32-bit linear file, which we'll load in as well. Okay, so they've rendered out and I've loaded up Nuke here. So here in our images folder, here are the two images we've just rendered from Maya. I'm going to drag those in. And then in our source images, we've also obviously got here our EXR and our JPEG. So this is the EXR, this is the JPEG, this is the scene referred, which obviously goes with the linear SR file, and the display referred, this one goes with the JPEG. Now remember, these two have both been rendered out linear OpenEXR. This original file was linear OpenEXR and this was 8-bit sRGB. So let's see what we get. Firstly, our original. You can see that's what we're getting. We come across to our original JPEG. That looks like that. And if you keep an eye on the image, you can see I'm going back and forth between the two, and they're both identical. The reason why they're identical in Nuke is that when we open up this one, you can see that Nuke is saying the input color is linear, and so it's not doing any conversion to linear. It's saying it's linear coming in, so it doesn't need to convert. This one, however, it says the color space coming in is sRGB. We know that is JPEG, and therefore it's converting it to linear. So both this and this are both coming in linear, which is what we would expect. Now we've taken that into Maya, both of these into Maya, we've linearized them in Maya, and we've then output them. So if we look at this now, so this will be 3 and 4, and we look at these two are also exactly the same. Obviously it's a little bit smaller if we go between these two, but you can clearly see the colors aren't changing, it's just zooming. So what we've successfully done is we've taken two different types of file, a linear 32-bit file and a gamma corrected 8-bit file. We've taken them into Maya. We've used Maya's color management system to feed them into the shader setup. We've then rendered it and then output both of them as linear OpenEXR, which is what you would want to do. So they are linear OpenEXR files, 32-bit coming out, and they're coming out with a gamut of the sRGB. Now we could have easily done a higher gamut if we wanted to, using the ACES or the ACES CG, but for this example we chose just to use the standard sRGB gamut. So you can see it works really well once you understand the way the color system works and the color management system in Maya. You can get very consistent results. So really that is as far as we want to go in this class. From here on out, we're going to be using that color management system for all our classes. So you're going to get more familiar with it as we go through and we do more shader building and more look dev and lighting. So if you have any questions about anything we've done, anything you feel we've missed, please let me know in the forums and we can talk further about it there. All these files, obviously, I'm going to have as part of the class, so you'll be able to use them and try them out. Try different things. One thing we haven't obviously tried is a log file going in through Maya's color management system, but I can guarantee it's going to work the same way. So it'd be great to see some examples of some of the color management that you would have done, taking it through from maybe a paint program into 3D and then out of the renderer into maybe a compositing tool. It would be interesting if any of you using other tools such as maybe Fusion or After Effects for compositing and just how that works and how that deals with the color management within those different applications. I'm guessing most of you though, however, are going to be using Nuke as it really is the industry standard. So as I said, any questions, please put them in the forums and look forward to talking with you on the forums and our next class. So until then, this has been Matt Leonard for FX PhD.